So welcome back, everybody, for the second lecture by Edward Witten. As you know, feel free to ask questions at any time. We'll be monitoring the chat. You can raise your hand or just ask your question. I guess that's it. The recording of this lecture will appear on YouTube afterwards if you want to watch something back. All right. So, Edward, I think the virtual floor is yours.
Well, thank you so much. So just as a reminder, what we did last time, more or less in the second half of the lecture after the Riesz-Leiter theorem, we defined relative entropy in quantum field theory. And I tried to explain the proof that it becomes only smaller when you make a region smaller. But unfortunately, we didn't really have time to explain why that's important and what applications it has. So the goal of today's lecture is to try to explain some examples, well, by no means have time for all the examples, of why what we were discussing yesterday is important. But as a preliminary, I really want to make contact between what we said yesterday and what is said about ordinary finite dimensional quantum systems. So the very first thing I'll do is to discuss relative entropy in a finite dimensional quantum system. I'll give you the standard definition in a moment. Or perhaps I mentioned it at the end of the last lecture. And then we're going to check that it's equivalent to Araki's definition. And then we'll proceed from there. So if you have a quantum system with density matrices rho and sigma, what's called the relative entropy between them is defined by this formula, except I think I just realized I have the minus sign wrong there. That should be plus. So the first term is just minus the von Neumann entropy of the system rho. And okay, as I said at the end of yesterday's lecture, we're going to make contact between this and Araki's definition of relative entropy. And then I actually concluded yesterday by sketching why relative entropy is positive. Here I got the sign right. So in quantum field theory, we don't really have density matrices. And by the end of these lectures, you'll understand more clearly why density matrices can't be a rigorous notion in quantum field theory. Instead, we define relative entropy in quantum field theory using the Tomita operator and the modular operator. So to make contact between the finite dimensional setup and what we did in quantum field theory, I want to show you what the more abstract discussion of the Tomita operator and so on would mean for a finite dimensional quantum system. And then we'll see that the abstract definition that we used in quantum field theory agrees with the elementary one for density matrices. So we start with the tensor product Hilbert space HA tensor HB, where we'll assume that the two spaces have the same dimension n. And we let A be the algebra of n by n matrices acting on HA. So an element of the algebra acts by A tensor 1. It acts by A on HA and it does nothing on HB. An arbitrary vector has the so-called Schmidt decomposition that we wrote last time. There's a Schmidt decomposition even if the spaces don't have the same dimension. HB, for what I'll say, HB could be bigger than HA, but the extra vectors in HB simply wouldn't appear in this decomposition, so they wouldn't play any role. So it's convenient to simply assume they have the same size. Then psi is such a decomposition where the vectors k in the first space and k prime in the second space are orthonormal bases of the two Hilbert spaces. Sorry, yeah, okay, that's true, but a generic vector has non-zero ck's. So psi is cyclic separating if and only if the ck's are all non-zero. That's true for a generic vector, and we'll proceed assuming psi is generic for the moment. I also will abbreviate the state which is j in the first Hilbert space times k prime in the second. That's just j comma k. So my next slide, I'm sorry to flash a bunch of equations in front of you, but I just want to make it clear that we could concretely define the Tomita operator in this setting and that it's elementary to do so. So remember, the definition of the modular operator was that S on an element of the algebra times psi is the adjoint element times psi. But here, the algebra we're considering is the algebra that only acts on the first vector space. That's analogous in quantum field theory to considering the operator of algebra of operators that only act within a given region. In quantum mechanics, we say the algebra only acts on one factor of the Hilbert space. So the definition of the modular operator was supposed to be this. And to make it into a concrete formula, pick any elements I and j in the set that labels the basis vectors. A general A, well, any A is a linear combination of elementary matrices that map vector I to vector j and annihilate the other vectors. So if we know what S psi does on all states of this kind, we'll know what it does on all states. So if A does this, then A dagger maps j to I and annihilates the others. So if psi is a linear combination, this should be ij. If psi is a linear combination, no, sorry, this is, okay. If psi is as I've written here, then A tensor 1 on psi. All that A does is maps I to j, so and projects the others to 0. So A tensor 1 on psi would be Ci times the basis vector ji, but A dagger times 1 on psi would be Cj times ij. So the definition of the Tomita operator says it's supposed to multiply a constant times ji to another constant times ij. So since Si is antilinear, when you divide by Ci, you have to complex conjugate it. So we learned that S psi on the basis vector ji gives Cj over Ci bar times the basis vector ij. Now, that wasn't terribly illuminating, but the reason I went through it was to make clear that this slightly abstract looking definition can be turned into a concrete formula for Si, for what Si does to basis vectors. The answer we got depended on the state psi, and that's inevitable. The definition of the Tomita operator does depend on the choice of a state. So we picked this maximally entangled state psi where all the coefficients were non-zero. And that was important because we had to divide by Ci bar. And that enabled us to define the Tomita operator on all states. Now, I went through that. It possibly was tedious and not much fun to try to follow that slide. But I went through that to show that we can concretely define S sub psi. Now, once we know Si, it's straightforward to compute its adjoint. And then delta psi is S psi dagger S psi. And if you continue with that computation, you'll learn that delta psi is one density matrix tensored with the inverse of the other, where rho A is the density matrix of the first system, and rho B is the density matrix of the second system. So, in other words, we have a state psi from which we can deduce a reduced density matrix, rho A or rho B for system A or B. And for this state, the density matrices are these. One is a matrix acting on A, one acts on B. Delta psi is an operator on the combined system. And the operator on the combined system, which is delta psi, is just one density matrix tensored with the inverse of the other density matrix. So that's actually roughly why Tomita Takasaki theory is important in quantum field theory. In ordinary quantum mechanics, you have density matrices. In quantum field theory, you don't. But some combinations do generalize. So there isn't really a good analog in quantum field theory of just rho A, but rho A tensor rho B inverse does have a rigorous analog in quantum field theory, which is the modular operator. Now, similarly, you can define the relative modular operator for two states phi and psi. And the same kind of computations show that the relative modular operator is the density matrix sigma A, which is the density matrix for phi on the A system, tensored with the inverse of the density matrix of psi on the B system. So the relative modular operator is, again, one density matrix times the inverse of another. But now, one density matrix is for the vector phi, one is for the vector psi. Now, the computations required to get these formulas are straightforward, but not too much fun to go through in a lecture. So they're very similar to this page. So if I was to, well, I have, in a previous lecture, I once did it. Wasn't sure how much the audience enjoyed those 4 slides, but in a series of 4 slides similar to this one, I went through all the computations. to get these formulas. Today, I decided to spare you, and well, you can read about it, for example, in my lecture notes, I think near the beginning of section 3, no, maybe section 4. But I decided not to actually do those computations in front of you, as they're not too they're elementary, but not too illuminating. Now, the formulas we got for the density matrices, okay. For this state, it's straightforward to trace out either the A system or the B system. When you do that, the coefficients get squared. So Ci is replaced by Ci absolute value squared, which leads to these formulas for the two density matrices. They have the same coefficients, but with different basis vectors, k and k prime, in the two spaces. So these formulas hold for any possibly entangled pure state of system A and B. So they make it obvious that rho A and rho B have the same eigenvalues and hence the same entropy. So that's an important fact about entangled states, entangled pure states in quantum theory. It's a fact that has no classical analog, because classically there's no notion of an entangled pure state. And we're going to need it in a second. Now, given the relation of the modular operator to the density matrices, we can compare Araki's definition of relative entropy to the one that's usually given in elementary quantum mechanics. So the relative modular operator, as I said, is one density matrix times the inverse of the other. So its logarithm is the sum of the logarithm of one minus the logarithm of the other. So if you use Araki's definition of the relative entropy, you'll get the matrix element in the state psi of a difference of two logarithms. Or in other words, you'll get this. Well, the expectation value in psi, the state psi, is the same as the trace with the density matrix rho AB. So I just used the defining property of a density matrix for the state psi to go from this formula to this one. The first formula here makes sense in quantum field theory. Well, with the logarithms written in terms of the modular operator. The formulas with density matrices are fine in ordinary quantum mechanics. This can be simplified because each of the operators acts on only one system or the other. So for the first term, we can do the trace over B because the identity is acting on B. The trace over B replaces rho AB with rho A. For the second term, we do the trace over A, reducing rho AB to rho B. But then using the fact I told you that the B system and the A system have the same entropy, we can replace this with this. And so we get the formula for the relative entropy that you'll most often encounter in the context of quantum mechanics. Now, one of the most important results in quantum information theory is that relative entropy is monotonic in this general setting of quantum mechanics. And that result is one of the milestones of quantum information theory. And it can be proved by matrix manipulations that can be inspired by what I said about quantum field theory yesterday. There's actually a version of this in my lecture notes, and I've presented the proof that way in a previous lecture. But today I decided to give a more physical argument, where I'm going to use the fact that the real world is described by quantum field theory, and therefore every quantum experiment is really happening in a quantum field theory. So I'm also going to use the fact that it's possible to do experiments involving quantum systems that are entangled at a distance. That's why quantum information theory is significant. So I consider two laboratories A and B in which quantum systems that I also will call A and B are being studied. I don't want to assume the system AB is in a pure state. It might be entangled with something else. C, possibly the environment, maybe some other experimental system. The only assumption I'll make about C is that it's outside the two laboratories. So the experimentalists studying systems A and B are actually studying A and B rather than mixing them up with C. So here's the setup. There are three systems, or maybe two systems in an outside environment, which are overall in a pure state. But we're going to just look at A and B, which might be in a mixed state. A mixed state is just an entangled state that isn't pure, necessarily pure. Now we're going to imagine a space-time region U tilde that contains lab B and a larger region U that contains both A and B. Neither one contains C. So U tilde is in green and U is in dark blue. Well, U tilde and U are both intended to include the purplish pink region A and B inside them. Now, if psi and phi are any two states of the world in quantum field theory, then monotonicity of relative entropy says that the relative entropy between the two states in region U is bigger or equal to that in the smaller region U tilde. Now I'm going to assume that psi and phi are such that they're identical except for the state of the experimental systems A and B and the outside system C. That means that in studying properties of A and or B, you can ignore everything else except A, B, and C. Now, you should ask whether such states psi and phi exist. As a mathematical statement, I'm confused when I think about it, but I feel it's clear the answer is yes, or it would not be possible to do experiments that exhibit quantum entanglement for separated regions. In other words, any experimentalist who claims to have verified predictions of quantum mechanics involving separated experimental systems has claimed to establish this state of affairs that I'm talking about, where the states that they're studying only differ by the condition of the experimental system and not by unobserved degrees of freedom, for example, in the experimentalist's body or in the rest of the laboratory. So somehow, an experimentalist who manipulates electron spins or whatever in different laboratories and studies correlations is able to establish states that only differ by the degrees of freedom that are being manipulated and studied. So that's the assumption I'll make. Then let rho AB and sigma AB be the density matrices of subsystem AB in the states psi and phi. Similarly, if you just look at system B, you have density matrices rho B and sigma B. By our assumption that we can ignore everything except the systems A, B, and C, the relative entropy in the region U is just the relative entropy between the systems A and B. And in U tilde, it's just the relative entropy between the two states of system B. So the relative entropy for AB is equal to or bigger than the relative entropy of B. So I feel that should be the proof. The proof I gave of relative entropy in quantum field theory is actually more obvious than any proof in finite dimensions. All I said was that when you make the region smaller, you're putting a constraint on the wave function so the energy becomes bigger. Now, you can imitate that with an argument involving matrix manipulations. But although I tried hard in my lecture notes, and you can look at the written version, to make that as transparent as possible, I don't think any argument is as transparent as the one in quantum field theory. So the proof I'd really like for this statement is the one I've just told you. That is true for every quantum system because every quantum system is part of a quantum field theory. But when I actually gave a lecture on the subject a few years ago and wrote up the written version, I wasn't comfortable with that argument. So I gave a more traditional mathematical argument that you'll find in section, I think, 4 of those lecture notes. Since rho B and sigma B are obtained by tracing out the system A, this result is often described by saying that relative entropy is non-increasing under partial trace. There's a slightly more general statement that it's non-increasing under any quantum channel, which means any manipulation that you can apply to a quantum system. But unfortunately, there isn't quite time in these lectures to explain that notion.
Can I ask a question?
Yes, please.
So I'm a bit confused. So what is exactly missing? Why you are being so careful by saying that we are not proving things rigorously? Because by invoking QFT, if I remember the QFT argument that you gave previously in lecture 1, you were using the fact that algebras were increasing monotonically, and this was leading to some constraint on delta. So yes. Here you are saying that this part of the argument is not obvious. So
well, you can look at. I tried to make it as obvious as I could for matrices in section 4.
Okay, I'll look. Yeah,
I chose not to give that argument. I chose to explain it this way today instead, because this is the argument morally that I really like. Not sure how rigorous it is. There is a mathematical version involving matrices. You have to compare matrix algebras of different sizes. And you can indeed imitate what I said. That's the way I tried to present it. Well, you can look at section 4 and see how you like the argument.
Okay, I'll look and then maybe I'll ask again on Slack. Thank you.
Sure. Okay. Or you could ask, well, we can have questions about this lecture tomorrow at the end of that lecture.
Sure.
Any other questions?
I have one question.
Yes.
The energy that you're referring to is the modular operator interpreted as a notion of energy.
Yes, logarithm minus logarithm of the modular operator.
Does that operator obey locality in some sense? Because
No.
we have question
No.
about mechanics and energy. Hamiltonian is approximately local.
No, it was, sorry. Actually, the analogy I made yesterday didn't involve logarithm. So no, the argument I made yesterday, I just took delta equals S dagger S and tried to explain that if you remove some states from the domain of S dagger S becomes bigger. So I actually didn't introduce the logarithm of delta yesterday. It's true that people sometimes do though. In fact, I'm about to explain a situation where log delta is local, so that's a good thing to do. But as you're suggesting by the question, that's exceptional. So positivity and monotonicity of relative entropy are among the fundamental facts about quantum entropy. And I'm just going to spend a couple of moments to explain some facts about entropy that are most easily deduced once you know about relative entropy. So here are a couple of facts we can deduce. First, consider a bipartite system. A bipartite system just means you have two subsystems, A and B, with density matrix rho AB. A second density matrix on the same system with the rho A tensor rho B, which I'll call sigma AB. It's equivalent to rho AB for measurements on just one of the two subsystems. Because if you make a measurement on just A, you could take a trace over B and reduce to rho A. In other words, another way to say it is that both of these density matrices, if you take the trace over B, will give the same rho A. So they're equivalent for measurements of system A and also equivalent for measurements of system B. But if you make a joint measurement of the two systems, you'll discover correlations in rho AB, which are absent in sigma AB. So sigma AB differs from rho AB by suppressing correlations between the two subsystems. Now, the logarithm of sigma AB is again a sum of two logarithms. So, well, first, the relative entropy between rho AB and sigma AB is non-negative. And then following the definition, we can write it like so. And then since the logarithm of sigma AB is has a sum of two logarithms, we get a formula like this one. And in this formula, the right-hand side is actually a sum of three entropies. The term with log rho AB is the definition of minus S of rho AB. And for example, the term with log rho A turns into S of rho A after taking a partial trace over B to reduce rho AB to rho A. So each term on the right-hand side is an entropy. So the right-hand side is this linear combination of entropies. And we abbreviate, very commonly people abbreviate, for example, S of rho A as just SA. So the right-hand side is this linear combination of entropies. And so its non-negativity says that the mutual information is non-negative. A statement that's also called sub-additivity of entropy. And one can show that the mutual information tells you how much you can learn about system A by measurements of system B. Unfortunately, that's another interesting point that we won't really have time to discuss in these lectures. Now you can do a similar computation for a tripartite system, a system of three components, A, B, and C, with the density matrix rho A, B, C. And now I will ignore the correlations between A and BC by defining sigma ABC to be rho A tensor rho BC, where, for example, rho AB is the trace over C of rho ABC, and sigma AB is the trace over C of sigma ABC, which is, in this case, for this one, is the same as rho A tensor rho B. So all density matrices for subsystems are defined by taking traces over the other subsystems. So monotonicity of relative entropy under partial trace tells us that if we trace out the C system, the relative entropy becomes smaller. But exactly as in the last discussion, these relative entropies are mutual informations. So this one is the mutual information between A and BC, because we ignored the correlation between A and BC when we defined sigma ABC. And the one on the right-hand side is the mutual information between A and B. So the inequality says that this is bigger than this. And after some rearrangement, it gives this inequality, which is called strong sub-additivity, and has many applications in quantum field theory and holography. So in these lectures, I'm going to tell you about two applications. One will be to the C theorem, and the other will be to the generalized second law of thermodynamics. So the first one will be today, but we won't get to the generalized second law until Thursday. So now we come to, well, topic 4 on the list I had at the beginning yesterday.
Ask a question about the previous slide.
Yes, please.
So all of this relies on the use of density matrices, or was that just for the?
Yes.
So you're assuming the density matrices exist?
These statements are rigorous in ordinary quantum mechanics, but these formulations are not rigorous in quantum field theory. I've told you the main statements in quantum field theory that are rigorous. The definition of basically relative entropy is rigorous in quantum field theory. But statements about density matrices and entropies are not rigorous. However, well, an example will be the proof of the C theorem later.
Okay.
Maybe we can discuss your question more fully when we get to that.
All right.
So I'll just briefly say that physicists working with entropies make manipulations that I think are very convincing, but aren't mathematically rigorous with the mathematical theory as it exists now. Basically, those involve situations where ultraviolet divergences cancel.
Thanks.
So going back to quantum field theory, in general, for a state psi in a region U, it's very hard to identify concretely the modular operator, or more or less equivalently, but less rigorously, the density matrix. But there's one case in which this can be done, and that example is very important for applications. That's the case that U is a Rindler space or wedge in Minkowski spacetime, and psi is the vacuum state, which I'll call omega. So the Rindler wedge U is defined by the condition that x is bigger than t, where x is, I really didn't want an absolute value here, sorry, I should have written that x is bigger than the absolute value of t, not the other way around. So anyway, the Rindler wedge in 2 dimensions is just this region. And if there are transverse coordinates, the Rindler wedge extends into the transverse coordinates. And they won't really play an important role in the discussion I'm going to give. So the Rindler wedge, regardless of the number of dimensions, you pick one space coordinate and you say that x is bigger than the absolute value of t, which gives you this type of region times rd minus 2 parameterized by some transverse coordinates, if there are any. Now, there's a rigorous approach to what I'm going to say to Bizignano and Wickman, which involves holomorphy of correlation functions. And you can find a brief synopsis of it in my lecture notes. But instead, today I'm going to explain what's an approach that's much better known by physicists, a path integral approach based on a presumed factorization of the Hilbert space as a tensor product where h left and h right are the degrees of freedom visible in the right and left Rindler wedges. So h left describes all degrees of freedom you can see over here, and h right describes all degrees of freedom you can see over here. So I've here drawn a real line in the Rindler spacetime. You can think of it as an initial value surface at time 0. So everything you can observe in this Rindler wedge came from initial data on the right half of the initial value surface. And everything you can observe over here came from initial data on the left half of the initial value surface. So we're going to think of the ground state of a quantum field as a function psi of 5x, where 5x is the field on the real line. And further, we'll think of phi as a pair of phi left and phi right, where phi left is defined on the left half of the line and phi right on the right half. So the ground state is a function psi of phi left and phi right. So The physics of an observer in the right Rindler wedge is governed by a density matrix appropriate for observations of phi right only. And we want to compute that density matrix. To get started, we first need a convenient representation of the ground state wave function, psi, which depends on both phi left and phi right. It's given by a path integral on the lower half plane with boundary conditions in which the boundary values phi left and phi right on the boundary are specified. Phi left over here and phi right over here. The path integral computes a wave function psi that depends on both phi left and phi right. Similarly, well, how would we make a pure state density matrix for this vacuum state psi? The pure state density matrix is just a bra times a ket. And we can make the bra or the ket by the same procedure. One of them is a path integral in the lower half plane, and the other one is a similar path integral on the upper half plane. And the black dots just divide the initial value surface into the right half and the left half. Now we want to take a partial trace that gives a density matrix for the right half only. That's accomplished by setting the fields phi left and the left halves of the picture to be equal and integrating over phi left. That glues together the left halves of the upper and lower boundaries. Now the path integral that we're doing looks like this. See, I took this picture and I glued together the left halves of the picture to say that phi left below in the lower half is the same as phi left in the upper half. And after gluing them together, I get like this. That opening angle should really be 0, but you couldn't see it. I drew a small opening angle just so you can see it in the picture. What we have now is a path integral in the whole plane, but there's a cut on the positive real axis, and boundary values are specified below and above the cut, and in general are different. So the path integral computes a function rho of phi right and phi right prime, where phi right prime are the boundary values above the cut, phi right are boundary values below the cut, and this is the density matrix. Sorry, this is the matrix element of the density matrix between a state given by phi right, initial state given by phi right, and a final state given by phi right prime. So that's the density matrix. But the same path integral can be understood in another way. I've simply drawn the same picture again of the whole plane with a cut in it, but I've drawn it in a way that emphasizes the rotational symmetry that the plane had before you took the cut. And now you can see that you can generate the cut plane by starting with a half line and rotating it by a 2 pi angle around its endpoint. So that gives us a formula for the density matrix. If R is the operator that generates the rotation, the density matrix is e to the minus 2 pi r. It's useful to write this on Lorentz signature. In Lorentz signature, R becomes the Lorentz boost operator k, so rho is the exponential of minus 2 pi k. Except we have to be careful what we mean by k. So here, we took only a half line and we were rotating the half line. So in this formula, k is rho is a density matrix acting on a state defined only on the positive half space where x is positive. So here k is acting as a Lorentz boost in the positive x region and doing nothing for negative x. So k is given by the usual formula for the Lorentz boost generator, except we only integrate over positive x. And in this formula, I've included the normal coordinates y perp, perpendicular to the Rindler wedge, which have been doing nothing but sitting there throughout the discussion. So this is a very rare case when you can make an explicit formula for a density matrix of a quantum field. And we'll use it near the end of this lecture in an application. Okay, as usual for charge generator, we define the charge by integrating only over space at a fixed time, which we can take to be time 0. But here we integrate only on half space. So you can go farther and find the Tomita operator. You see, in fact, well, you can go further and find the Tomita operator and the modular operator. But for that, I refer to my notes. We're only going to use the density matrix. And so I'm only going to present the derivation as far as this. I will, though, say a word on what we might learn from this formula. Because of the factor of x, if there were no factor of x here, this would be the Hamiltonian, except only integrated on the right half space. So without the x, this would be the operator that measures the energy in the right half space. With the x, it's a little bit less obvious what it does, but one thing you can say is that if an object is localized near x equals L for some L, then for that particular object, K is more or less the same as the Hamiltonian H times L. So for a localized object that's at large x compared to its size, K is just L times the energy. And for such systems, Rho is like a thermal density matrix, but with a position-dependent temperature. In other words, for an object at a position L, the effective temperature is 1 over 2 pi L. So at a big distance from the boundary of the Rindler wedge, the effective temperature is small, but near the boundary of the Rindler wedge, the temperature blows up. Now this loosely thermal nature of the state, not thermal with a conventional Hamiltonian, but quasi-thermal, accounts in this example for the complete entanglement predicted by the Rho-Schlieder theorem. The Rho-Schlieder theorem predicted to us that everything in the right wedge should be entangled with something in the left wedge. Well, to say it differently, the Rho-Schlieder theorem said that the density matrix for any region is invertible. And now we computed the density matrix and found it was invertible. So e to the minus 2 pi k can have very small eigenvalues because k can have very large eigenvalues. But e to the minus 2 pi k is a strictly positive operator. So that's what was predicted by the Rho-Schlieder theorem. So this is the answer we found for the density matrix is a concrete illustration of the Rho-Schlieder theorem. When we discuss the Beckenstein bound, the analogy between K and L times H will be important. Now,
can I ask I'm a bit destabilized, Edward. So, because in your first lecture, you said very strongly that we are not allowed to think that the Hilbert space is factorized. We are not allowed to think of density matrices. So now we went back to the density matrices that we all thought about for a long time.
Yes.
So what is the morale of the story? I guess there should still be some kind of stop signs. I mean, if you only think in terms of density matrices, are you going to go wrong at some point? Or is there some book which says, okay, when it's allowed to use density matrices and when we should not be using them? So what's the morale?
I do not believe it's completely understood. So statements about relative entropy are rigorous. And I sort of explained the main rigorous statements yesterday. Statements about density matrices are not so rigorous. Okay. So, people in operator algebras who develop the rigorous theory tend not to use all the structure of quantum field theory. For example, okay. Well, one symptom of the fact that density matrices aren't rigorous, actually, this is something I was about to say anyway, is that entropies are ultraviolet divergent in quantum field theory. And so, I mean, the non-rigorous nature of density matrices is tied to the ultraviolet divergences. And I think you have to use a physicist's judgment about what's true despite the ultraviolet divergences. And of course, that, for example, that's highly dimension dependent. Whereas the rigorous theory, okay, there's a whole community of mathematical physicists who develop rigorous theorems about some of the things I've told you about, but they tend to never input anything that's dimension dependent about the nature of the ultraviolet behavior. So you're kind of on your own as a physicist, and we'll make some statements later on. For example, in 2 dimensions, well, let's get back to it after we discuss some ultraviolet divergences.
Okay.
So we were about to get to one, actually. I was going to say the following. In many developments, you want to divide space into 2 regions, A and B. I've drawn a case where B is compact and A is not. And then you take a pure state like the vacuum. But if you restrict it to subsystem A or B, well, if it were a lattice system, it would be correct to say it has a density matrix in system A and B. As we've discussed, that language isn't completely rigorous in the continuum theory. But nevertheless, you'd like to consider the entanglement entropy, S of rho A, which would equal S of rho B for a pure state. And it's actually important to consider it. Now, It's actually ultraviolet divergent, as was apparently first noted by Raphael Sorkin in early work on black hole entropy. And we'll get back to that on Thursday. But for today, I'll just say that the ultraviolet divergence comes from high energy modes near the boundary between regions A and B. I'm taking, in the picture, these are meant to be spatial regions at time zero. Associated to them are space-time regions, they're domains of dependence. But in this picture, I just mean to draw spatial regions. And if you try to calculate the entropy of the density matrix in one region or the other, then you get an ultraviolet divergence that comes from high energy modes near the boundary between regions A and B. And since it comes from high energy modes near the boundary, it's proportional to the area of this boundary. That's in contrast with relative entropy, which is completely free of ultraviolet divergences and is quite rigorously defined mathematically. So the ultraviolet divergences in the entanglement entropy are highly dimension dependent. We'll do an explicit calculation in 2 dimensions in a little while. Now, many important developments have shown that one can draw important conclusions from combinations of entropies in which the divergences cancel. But as of 2021, those arguments are not mathematically rigorous. But of course, you shouldn't be scandalized. Most of what we do in quantum field theory isn't mathematically rigorous. Now, I'm going to explain an important development that, 1, involves entanglement entropy in the vacuum between different regions of space. 2, depends on strong sub-additivity of entropy, which I've spent a lot of time explaining. And 3, involves ideas similar to what we just used in computing the density matrix of Ringler space. And here I have in mind the reinterpretation and proof by Cassini and Huerta of the Zamolodchikov C theorem, which says that the central charge can only decrease along renormalization group flows. The initial proof of Zamolodchikov was in 2 dimensions, and the original reinterpretation by Cassini and Huerta was also in 2 dimensions. And I'm only going to explain the 2-dimensional version. There are versions of this argument in 3 and 4 dimensions. Not yet in 5 or 6 dimensions. So as a preliminary, we'll consider an interval that I'll call curly L of length L in 2-dimensional Minkowski space. So I've drawn a line interval curly L, it has length L, and I've also drawn its domain of dependence, which is that green diamond. What that means is that all the physics in the green diamond is determined by initial conditions on L. Well, that's true classically, and it's also true quantum mechanically, with different levels of rigor and different versions of the statements. Now, by Lorentz invariance, the entropy of the quantum fields for measurements in the region D can only depend on the length of the interval. So I'll call it S of L. And we're going to compute that in a 2D CFT, where C left and C right we'll assume for simplicity to be equal and equal to what I'll call C, the entropy is C over 3 times the logarithm of L divided by cutoff. Epsilon will be an ultraviolet cutoff. So this will be an example of the fact that entanglement entropy is ultraviolet divergent in quantum field theory. In 2 dimensions, well, if it wasn't cutoff dependent, it would have had to have been a constant, because since entropy is dimensionless, it can't depend on the length L, unless it can also depend on a cutoff. Epsilon, by the way, is a length cutoff, not an energy cutoff. So epsilon is a small length that we think of as a cutoff. Epsilon would be a lattice spacing if you made a lattice approximation to the theory. Anyway, we'll get back and prove this formula later, but first we're going to use it. So a consequence of this formula is that the central charge is 3 LD by dl of the entropy. Now, I've drawn, this is meant to be, this point at the vertex is meant to be the origin in 2-dimensional Minkowski space. U and V are meant to be light cone coordinates. So this is meant to be a light ray parameterized by U, and this is another light ray parameterized by V. I think I drew an angle a little bit bigger than pi over 2, which it was meant to be. And then I've drawn some points U and U prime and also V and V prime on the 2 light rays. And in light cone coordinates, the distance between 2 points is the square root of the separation in U times the separation in V. So for example, the line labeled B has length square root of UV. This point has V equals 0, this has U equals 0. So the formula just reduces to the square root of UV. And the one labeled ABC has length the square root of U prime V prime. Now for simplicity, let U and V be equal to R and U prime and V prime equal to R prime. So B has length R and ABC has length R prime. The endpoints of the non-geodesic path AB are separated. Well, you see, from the when I say the non-geodesic path AB, I mean the path that goes from here to here. I've drawn a straight line. If you go from A, if you take A and then B, that's not a straight line. But you could take a straight line between the two endpoints. If you want to know what's the region of space where you could predict the physics from initial data on A and B, well, you have to take the domain of dependence, but that's the same as the domain of dependence between the two endpoints. So the length of the straight line between these two endpoints is the square root of V prime U, which is R prime to the 1/2. So that's the geometry we're going to use. I hope I didn't make it too confusing. Now in this picture, which I also hope is big enough that you can see it now, I've labeled 3 intervals A, B, and C. So the entropy of a field restricted, quantum field restricted to B, or equivalently its domain of dependence, is what I call SB, and that's the entropy of the length of B, which is R. If you restrict a quantum field to AB or BC, the entropy SAB or SBC is given by the length from this point to this point, or from this point to this point. And those lengths are both the square root of R prime. So these are each equal to the S of the square root of R prime. Finally, if you take the whole region A, B, C, well, we could replace this non-geodesic path by a straight line labeled ABC. And its length is R prime. So the entropy of the combined system is S of R prime. So the inequality of strong sub-additivity becomes this one. And well, it can be expressed concretely in terms of S of R, the function S of R at different values. Now, if you set R prime equal to R plus A, first of all, this will be 0 at A equals 0, and its derivative with respect to A is also 0. But you can take the second derivative. The second derivative is the first non-trivial term for small a. So for small a, the inequality becomes this one. In other words, from strong sub-additivity of entropy, we've deduced this inequality on the second derivative of the entropy. This can be interpreted as a version of the Samologikov-C theorem. So as I've remarked and will also explain shortly, in the case of a CFT, the central charge is 3LD by dl of S of L. So let's define a C function by C of R equals 3RD by dr of S of R. The point of that definition is that C, defined that way, agrees with the standard C when you're in a CFT. So what we proved was that the C function is monotonic. In other words, the inequality we deduced from strong sub-additivity precisely says that this C function has a negative derivative. So to turn this into a version of the Samologikov-C theorem, all we need is to verify the statement that C of R, if you're in a CFT, coincides with the usual central charge C. Once we know this, the monotonicity of C of R then implies, for example, that in the case of an RG flow from one CFT in the UV to another in the IR, C cannot increase. I think with more care, one can prove that it's a strict inequality, but as I've done it so far, we only get any inequality. So to justify the claim that in a CFT, S of R has the claimed relation to the central charge, we're going to use the replica trick, which is by far the most common way to actually compute entanglement entropies.
May I ask a question before? So in the previous argument, we used that when we do boosts, right, of these diamonds,
Yes.
the dependence of the entropy is always on the Lorentz invariant size of the diamond.
Yes.
And with the same UV cutoff. So we are assuming that there is some UV cutoff which is fully Lorentz invariance, right?
Yes. Right. That's correct. That's why we can't make this argument for lattice theory, or part of the reason.
Okay, thank you.
By the way, we didn't try to define SA or SC, which would have been bad because those are null segments. So we only defined entropies. SAB is okay because the endpoints are space-like separated.
Yes.
Okay, now I still have to explain, we have to compute the entropy in a CFT. And by far the most common way to actually compute entanglement entropies is called the replica trick. So we rewrite the definition S equals minus trace of rho log rho as minus d by dn at n equals 1 of the trace of rho to the n. Then the usual procedure is to compute trace of rho to the n for integer n, analytically continue to a holomorphic function of n, and evaluate the derivative at n equals 1 to get the entropy. So any questions about that?
I mean, if I have rho in the integer points, rho n, does the analytical continuation to the complex plane of n is unique?
It's not completely unique, but it's unique if you impose a boundedness condition in the right half plane.
Thank you.
So for a finite dimensional quantum system, this would be rigorous because trace of rho to the n would be analytic in a half plane. Well, for a finite dimensional system, it's an entire function. But even for an infinite dimensional quantum system, it's entire and a half, analytic and a half plane, and that's enough to make the analytic continuation unique. In quantum field theory, well, there's definitely less level of rigor. So
Can I ask a question about that? A question about the same subject.
Yes.
Before we related rho to the boost operator,
Yes.
which doesn't have bounded eigenvalues as far as I know.
Yes.
So it's not clear that this function, this function is bounded.
Yes.
Right?
We didn't normalize rho to have trace 1. And you can't in quantum field theory, actually. That's part of the non-rigor. So I was a little bit cavalier about the overall normalization of rho, which actually will come up in a moment. We're going to run into an ultraviolet divergence.
I also believe there is a paper by maybe Cardi and Calabrese where they try to compute the rho for disjoint, two disjoint intervals, and the analytic continuation in n did not exist, or they could not find it. And
I think it's more likely they couldn't find it. First, we need a reasonable way to understand the density matrix of the theory for measurements in the region L. So this has a nice path integral representation that's quite similar to how we studied Rindler space. I hope you can understand the picture. I've compressed into one picture what we explained in several steps for Rindler space. So the path integral in the lower half plane and the path integral in the upper half plane would construct the pure state density matrix of the vacuum. But then we glued together the bra and the cat in the region outside of L that we want to trace out. So we made the gluing now to the right of L and also to the left of L, and we only have a cut along L. So we have the plane with a cut along L. So that picture represents the density matrix. Now, how would we compute, for example, the trace of Rho cubed? Well, the trace of Rho cubed, you can write it as a sum over matrix elements. And the important thing is that this second index of each factor of rho is equal to the first index of the next one, going around in a loop to get a trace. So we have to start with 3 copies of rho and then set the second index of one copy equal to the first index of the other. So here are 3 copies of rho. Each one is represented by a path integral in a cut plane. Then we have to make a gluing, which will identify the matrix element of rho above the cut in one copy, with the matrix element below the cut in the next copy. So I've tried to picture the gluing here. The purple lines show regions above the cut in one copy that we glue to regions below the cut in the next copy. By the time we've made that gluing, we've built a new Riemann surface that can be described as a triple cover of the original complex Z-plane branched over the endpoints of the interval L. We can describe this Riemann surface by an equation, y cubed equals z cubed times z minus L cubed. And the path integral of the original CFT on this new Riemann surface will compute trace Rho cubed for us. To compute trace Rho to the n, we just replace 3 with n and look at this Riemann surface at the bottom. But there's a more convenient way to approach this. Instead of doing the path integral of the original CFT on a new n-sheeted Riemann surface, we take n copies of the CFT and do the path integral on the original spacetime. How do we take the branching into account? We introduce a twist field theta that cyclically permutes the n copies. Its adjoint theta bar cyclically permutes them in the opposite direction. So theta and theta bar create the desired branching of the complex plane. So I've drawn the complex plane with an insertion of theta and an insertion of theta bar. Now you're supposed to imagine we have n copies of a CFT, which locally corresponds to n sheets, an n-sheeted cover of the Riemann surface. But when you go around theta, the n copies of the CFT are cyclically permuted. When you go around theta bar, they're cyclically permuted in the opposite direction. If you went around the big circle, they're not permuted. So theta and theta bar create the desired branching of the complex plane. So trace Rho to the n is just the vacuum excitation value of the 2-point function theta theta bar in a CFT which is n copies of the original CFT. In general, such a 2-point function in a CFT is L over epsilon to the minus 2 delta, where delta is the dimension of the operator theta. So it's the sum of the left and right conformal dimensions dl and dr. And epsilon depends on how the operator theta is normalized. But in our case, epsilon will be a UV cutoff. In the present example, I'll explain in a moment that dl and dr are c over 24 times n minus 1 over n. So delta is c over 12 times n minus 1 over n. And the 2-point function is given by this formula. So the entropy, which is minus d by dn at n equals 1 of this expression, is c over 3 times log L over epsilon, as promised. So the only thing we need to complete the argument then, I use this value for the dimension of the operator, and we have to check that. So we remember the operator state correspondent of CFT. Here's the plane with an operator inserted. That's conformally equivalent to a cylinder with a state in the far past that corresponds to this operator. Now, an operator of dimension delta corresponds to a state whose energy is delta minus c over 12, assuming the cylinder has circumference 2 pi. The minus c over 12 is a Casimir energy. We want to use this formula in a CFT that's n copies of the original CFT. So the value of c we have to use is c sub n, which is just n times c. And the state we're interested in is the one created by the twist operator. So that means locally we have n copies of the original CFT, but when you go around, they're permuted. So effectively, we have one copy on an n-fold cover of the circle. In other words, we have a single copy of the CFT on a cylinder whose circumference is n times bigger. That reduces the Casimir energy by a factor of n. So the Casimir energy of the state is minus c over 12n instead of minus c over 12. So the formula for delta becomes that the energy minus c over 12n is delta minus cn over 12, where cn is n times c. So we get the answer for delta, the dimension of this twist field. And that leads to the formula for the entropy ultimately. Now, of course, the Cassini-Huerta proof of the C theorem was not the first one. The theorem had already been proved by Zamolodchikov. But the proof is especially interesting because it captures the idea that RT flows are irreversible because the number of degrees of freedom related to the entropy is going down. Also, it's been possible to generalize the proof to 3 and 4 dimensions. The 3-dimensional case is particularly noteworthy because there's no other known proof in that dimension. In 3 dimensions, the proof is rather similar to what I've explained, but it's longer. The main difference is that you have to consider not just 3 regions, but n of them, and use strong sub-additivity, not just once, but many times. In 4 dimensions, one needs to use some essentially new facts. I will explain the necessary facts on Thursday, but unfortunately, we won't have time to go back and explain the application to the A theorem. In 3 dimensions, what plays the role of C is the entanglement entropy of a disk of some given radius L. In the case of a CFT, you can show using the replica trick that the disk entanglement entropy is related to the sphere partition function, which has been called F. So the 3D analog of the C theorem has been called the F theorem. So maybe I'll say one more thing about this. I want to say a word about the formula for the entropy of a region in 2 dimensions. So first of all, it has the advertised ultraviolet divergence. Epsilon is a short distance cutoff. But notice that the ultraviolet divergent part is independent of L. That's a special case of the following. There's a fact I already said before, but it's sufficiently important, I want to say it again. Consider any region of space and its domain of dependence, D. The ultraviolet divergence in the entropy of W, which is the same as the divergence in the entropy of D, comes from high energy modes near the boundary of region W. So the ultraviolet divergent term is proportional to the area of the boundary. In 1 + 1 dimensions, the interval has a boundary that consists of precisely 2 points, independent of the length. And because the boundary didn't depend on L, that's why the ultraviolet divergence is independent of L. Now, from what I said about the area, the entropy has a power law divergence that depends on the dimension. And usually to make interesting statements, you have to consider combinations where divergences cancel. And as I've said, the rigorous mathematical theory is developed without the kind of knowledge that would go into being able to make that kind of statements. So even a relatively simple case like this one, which only involves a logarithmic divergence that we feel we understand and know how to cancel. Well, where did I even write it? Okay, this statement here is not rigorous mathematically with any mathematical theory that's been developed to date. It's hard for it to be because, well, it's physically sensible in this dimension because the divergence is only logarithmic. But anyway, there's much more than is true than is known in the mathematical theory. Since that's true, you could ask me why I started with what was rigorous. Well, I thought it was interesting that there are highly non-trivial statements you can make quite rigorously, of which the one that fascinates me most is the monotonicity of relative entropy. So that completes what I'll say about this, and there's just one more brief topic I want to explain today. I hope we still have time. I think it'll take another 5 minutes or so, but maybe it's a good time to stop if there are any questions.
So just to confirm, I guess this was your point, but so there is no version of this Cassini-Huerta construction using finite quantities.
Oh no, there's no known version. It's an interesting challenge. We can express this in terms of mathematically right now, or possibly to improve the mathematical theory.
Can I reformulate my question about Rennie?
Yeah.
I fully agree with you. What you said is absolutely correct, that from integer n under the circumstances which you explained, Rennie entropy can be continued. On the other hand, if I consider asymptotical expression, let's say I calculate the entropy of large block of spins, and if I concentrate my attention only on the leading term, then Stokes phenomena can happen. And entropy can scale differently for different values of scale with the size of the block differently as a function of n. And then the analytical continuation with respect to n might become problematic.
I think there's no guarantee you couldn't run into trouble. So
I'm saying, yes?
I'd like to say that with gravity, in the last year, very interesting cases have been discovered where simple statements are not true. And entanglement, the replica trick has to be used in a more sophisticated way.
I also sent through chat the spin chain where the Stokes phenomena happen. So for different values of n, the Renyi entropy scales differently with the size of the block. So thank you for explanation.
Anyway, the replica trick is extraordinarily useful, but use it with caution.
I agree, yes, thank you.
I don't disagree with that. I think there's a question from Zohar, or there was.
About the twist operator.
Yes.
Well, the twist operator is not unique. I believe that the construction you presented goes after the ground state in the twisted sector.
That's right. Yes.
But why is that justified mathematically?
It's the lowest dimension operator.
Well, I can dress the twist operator by any operator in that twisted sector. Why would I make that choice?
It wasn't motivated to that. I mean, the picture was just geometrical. We were trying, in other words, we didn't need to introduce the twist operator. What we wanted was the partition function of the original CFT on an n-fold cover of the plane. And we could have done it that way. So the twist operator we want to use is the one that expresses the partition function of the original CFT on the n-fold cover in terms of a two-point function of the twist field on the base.
I believe my question would also exist in that language. It would be a question about how do you define branch points. You need to put boundary conditions. So my question is the same as in any formulation. It's a question about how do you deal with the boundary conditions of the entanglement interval.
Well, what you want to do, if this were a lattice theory, you'd put no boundary condition.
Right, but in QFT,
the analog of no boundary condition is use the vacuum vector there.
But in QFT, it's an inherent ambiguity, and I do not understand how to deal with it. Anytime you try to define correlation functions of twist operators or twist surfaces, like they do in this literature, you encounter these issues, and I don't understand how to deal with them canonically.
The burden of proof would be to argue that you don't want to use the one of lowest dimension, which is the most generic. So in other words, suppose you had a lattice cutoff. Suppose you're able to develop this starting from lattice cutoff. Well, a lattice cutoff would try to give something generic. And therefore, the lowest dimension one would appear with a non-zero coefficient.
Okay.
So I can't promise you won't run into trouble if you do something, but it's amazing how powerful the replica trick is. You really shouldn't expect to run into trouble. Keep it. Don't assume you won't run into trouble, but also don't assume you will. The simple statements are actually very powerful.
Well, another problem is that Zamolodchikov's C function was stationary at the fixed points, and this construction does not lead to a stationary function. That's also alarming because it defeats an RG interpretation. The first derivative of Zamolodchikov's function with respect to the RG flow was vanishing,
Yes.
which is not the case here. I believe this makes it questionable.
Well, I think it's a very beautiful unified approach in 2, 3, and 4 dimensions.
Can I ask a question? So you said this argument has not yet been generalized, but I was just wondering if perhaps one simple piece of it was, I meant made rigorous, which is the definition. So S of L cannot be rigorously defined because it's divergent, but there was this particular derivative of S of L.
Yes.
Which was finite by inspection because it cancels the log. So it means that if this theory ever to make sense rigorously, there has to be some rigorous construction of this quantity, which is the derivative of S, some sort of like.
So, yes.
Is there such a thing? Did mathematicians come up with a definition?
They can't because they don't do things. See, we had to know something about the ultraviolet behavior in 2 dimensions to say that the divergence was only logarithmic. And I wish that people tried to develop a mathematical theory where you inputted such assumptions about the short distance behavior, but the people actually working on operator algebras don't do that. So
there has to be some difference between operator algebras in different dimensions, and they don't know how to quantify
They don't incorporate that, I would say. Yes, that's my understanding.
Okay, thanks.
Now,
There is actually a question on chat as well.
is there another question in the chat?
Yeah, Dean, maybe you should just speak up because it was supposed to be informal.
I can ask. In quantum mechanics, there are definitions of relative Renyi entropies.
Yes.
Do they have monotonicity properties that can constrain RG flows?
Yes. Oh, sorry. They have monotonicity properties in quantum mechanics. And not only that, they can be proved by essentially the same argument as for the ordinary relative entropy. In fact, for one version of the Renyi relative entropy, there are different things people call relative Renyi entropies. For one version of it, the proof is actually in my lecture notes. And there's a paper by Nima Lashkari who explained the proof in a similar proof for a different version of the Renyi relative entropy. So they are monotonic. That hasn't had applications in quantum field theory that I know about. I'm not saying there can't be, but it hasn't happened that I know.
Thanks.
So one comment, which we'll get back to Thursday, is that in black hole thermodynamics, it's important that the UV divergence in the entanglement entropy is proportional to the area of the boundary. And that's important in understanding quantum corrections to the entropy of a black hole. So there's one more topic I wanted to explain today. I know we're a bit over time, but we did have a lot of questions, so maybe it's okay to go on a little bit.
It's fine.
Okay, thank you. So Beckenstein, so my last topic is the Beckenstein bound. Beckenstein motivated his bound by a heuristic argument involving black holes. I'll mention it Thursday. But the bound he proposed is supposed to be a statement about ordinary quantum field theory without gravity. So I'm going to discuss it just as a statement in quantum field theory. So for us, the Beckenstein bound is the statement that in quantum field theory without gravity, there is a universal inequality between the size R, energy E, and entropy S of a quantum system that takes this general form with the universal dimensionless constant K. So Beckenstein proposed something like that in 1980. Now, there are two questions that come immediately to mind. One is whether the conjecture is true, but another is whether the inequality is interesting. And for years, there was reason to be skeptical on both counts. So on the question of whether the Beckenstein bound was true, it seemed trivial that it couldn't be true in general. Consider a theory with n elementary particles all of the same mass. For example, you could consider a free field theory. Consider a system consisting of a box with one particle inside it. The entropy seems to be at least log n from the choice of one of n possible particles to put in the box. But the size and energy of the box don't depend on n. So it seemed clear that the entropy isn't upper bounded by size times energy with any universal constant that would hold for all quantum field theories. On the other hand, if true, is the Beckenstein bound interesting? Can we think of a system where the bound is close to being violated? Well, consider a system made of massless particles. If the particles are massive, that goes in the wrong direction because it increases the energy without increasing the entropy. For example, take a box of size R containing massless particles at temperature T. In 3 space dimensions, the number of particles in the box is of order RT cubed, and the entropy is of the same order. The energy is R cubed T to the 4th, up to a constant. So the Beckenstein ratio S over RE, in which we want an upper bound, is of order 1 over RT. Now, if RT is much bigger than 1, the notion of a thermal gas in a box makes sense. But in that case, the Beckenstein ratio is parametrically small, and the Beckenstein bound isn't really interesting. It's satisfied by a wide margin. Can we find a system where the Beckenstein bound is interesting as well as true? While keeping many particles in the box, but assuming the particles are not in thermal equilibrium, makes matters worse because it lowers the entropy for given energy. To make the Beckenstein bound challenging, we need to reduce the number of particles, which we can do by lowering the temperature. The best case is the box just contains one or a few massless particles, or in other words, the temperature is 1 over the size of the box or less. But a box containing just one or a few massless particles will weigh more than the particles it contains. In estimating the Beckenstein ratio, we can't ignore the mass of the box, which might have been unimportant for a large box, but is important if the box is almost empty. Including the mass of the box goes in the wrong direction again and makes the Beckenstein bound uninteresting. So in other words, the case that the Beckenstein bound is interesting is the case of a single particle without a box. But what sense does the Beckenstein bound make in that case? In other words, what's the entropy of a single particle? And for that matter, what's the size of a system consisting of a single particle, which is also a murky notion in quantum mechanics? In other words, when we try to go to a regime in which the Beckenstein bound is interesting, the statement of the Beckenstein bound does not seem to make sense. But amazingly, Cassini was able to give a precise definition to the terms in the Beckenstein bound and to prove it. He interpreted the Beckenstein bound as a simple statement of positivity of relative entropy. So he considered the vacuum state omega of an arbitrary quantum field theory and any other state psi. The goal is to prove that the Beckenstein bound is valid for the state psi with the correct interpretation of the terms. First, he divided space into the two halves of positive and negative x, where x is one of the spatial coordinates. The corresponding division of space-time looks like this in a two-dimensional picture, where I only draw x and t. So the Rindler wedge U is the domain of dependence of the positive x-axis, or the region where x is larger than t in absolute value. So the domain of dependence of the region of positive x or negative x at time zero, really. Those are the right Rindler wedges we studied before. So now Cassini considers the density matrices, rho, psi, and sigma omega, of the states psi and omega reduced to the region U. That means where one only considers measurements in region U. The relative entropy between them measures how well psi and omega can be distinguished by someone who only makes measurements in this region. So here I'm using the language of density matrices, though von Neumann algebras are more rigorous. So let's compute the relative entropy. So this was the definition, and it's finite in quantum field theory, but each of the two terms is separately divergent. So Cassini added and subtracted something to write the relative entropy as the sum of two terms that are both finite. So one term is minus the difference of entanglement entropies between the state psi and the vacuum omega. So it's equal to S omega minus S psi, or minus the difference of entanglement entropies. So the area law divergence cancels out when we take this difference. The area law divergence comes from the short distance behavior. It's the same for all states. So although entanglement entropy is divergent, the difference of entanglement entropy between the state psi and the vacuum is finite. So this term is a finite entropy difference. To evaluate the other term, we remember that if O is any operator, its expectation value in the state psi is the trace of rho times O, and its expectation value in the ground state is the trace of sigma times O. We use that with O equals minus log sigma, and we remember that we showed before that sigma equals the exponential of minus 2 pi k. So minus log sigma is 2 pi k, which is 2 pi times this integral of x times t00. So the second term is the matrix element of 2 pi k in the state psi minus the same thing in the state omega. Now, one of the questions before had to do with the fact that I hadn't worried about the overall normalization of exponential of minus 2 pi k. You could multiply by a constant here. It would become an additive constant when we take the logarithm, and it would cancel out in this difference. So the difference that we're discussing is independent of that normalization. That difference is the integral over the right half space of the expectation value of x times t00 in the state psi minus the same thing in the vacuum state. T00 is usually regularized to make the term with the vacuum state 0. So I haven't written that second term. But the formula naturally gave the difference of matrix elements in the state psi and in the vacuum. So the choice of regularization of T00 cancels out in that difference. Let's define curly E to be this expectation value in the state psi of the integral of x times T00. Cassini's insight is related to what I told you before. If psi is a quantum state that describes a system that intuitively is localized almost entirely in the right Rindler wedge, and that has size r and energy E, then curly E is at least E times R. So he proposed to use the quantity curly E, which is rigorously defined for all quantum states, instead of Beckenstein's heuristic E times R. And he used delta S, the difference in entanglement entropies between the state sign and the vacuum state omega, to stand in for the heuristic entropy S in the Beckenstein proposal. The positivity of relative entropy says that curly E is equal to or bigger than delta S over 2 pi, with equality only if psi is the vacuum state. And that's Cassini's rigorous version of the Beckenstein bound, valid for all quantum states. To illustrate the fact that this discussion goes way beyond the classical realm, let me point out that it's possible for the left and right-hand sides of the formula to be negative, but still the inequality holds. So that completes what I have to say for today. Thank you.
Thank you very much.
Thank you.
So, thank you. And see if there are other questions.
Maybe can you please comment on this issue when you have multiple types of particles? How does this escape here? Maybe it's obvious. But,
Well, it's a good question, which I think was discussed a little bit in Beckenstein's paper. You can't ignore pair creation. So you put a particle in the box. Okay, you might have thought that it was exponentially unlikely. Okay. The particles are massive, so for a particle-antiparticle pair that you didn't create to be there, it seems very unlikely. But if you have very many particles, it becomes more likely. So since the entropy was only log n, to make the entropy large, we need n to be exponentially large. And when you make n exponentially large, the number of particles that are there at random in vacuum fluctuations becomes significant. And it becomes hard to distinguish the vacuum from the state where you actually put a particle there on purpose.
so which side? So the S defined by Cassini will still grow or will not grow because
Right. So okay, take Minkowski space, start with the vacuum, take a theory with n particles, put one particle of mass m, a distance at x equals r, and that'll make a system whose relative entropy with the ground state, well, its entropy difference with its relative entropy with the ground state will be what you think it is if n isn't too big. But if n is exponentially big, there'll be a log n, and you'll think that the relative entropy is log n minus energy times r. Energy will be the mass of the particle, r is where you put the particle, and the entropy difference seems to be log n. So you get log n minus mass times r. And that formula will be correct if n isn't too big. If you make n so big that log n completes with m times r, what that means is that n times the exponential of minus mr is no longer small. And the exponential of minus mr is the probability that by chance there was a vacuum fluctuation that created a particle here with its pair being in the other Rindler wedge. So where these species bound would have led to an apparent contradiction is where particle creation, particle-antiparticle pairs in the vacuum, where one is in the region you're looking at and the other is behind the horizon, becomes significant.
I see. Thank you.
Sure.
Any more questions? I see nothing.
I do have a sort of question or comment, since many of the questions discussions were about this divergence of the entanglement entropy. So this divergence, for example, I think, but of course, correct me if I'm wrong, in CFT, if the CFT comes from some lattice model or from one-dimensional quantum system on a lattice, the epsilon should be the lattice spacing. So we have like sort of a regulation of this UV divergence. But we also have some indications that in low-dimensional models, in toy models, that this divergence can be regulated, for example, in string theory, where in some toy models, you find that the divergence is due to string coupling, so to the dilaton, to a divergence of it's not divergence, sorry. Instead of having like 1 over epsilon, one has like 1 over square root of G string of x1, G string of x2, where x1 and x2 are the 2 endpoints of the interval. And so we have examples of that. Of course, they're completely non-rigorous and they're toy models.
Yes.
And
I think that's interesting. Yes.
Yeah, I think that's quite interesting. So I wanted to mention it.
I tried to get something like that once, but failed. And what I tried to do, I looked at open strings in Rindler space, tried to compute the entropy using an entanglement trick, and got answers that weren't really physically sensible.
I see.
They were
I see.
finite. They were finite, but they weren't really physically sensible. But well, I didn't know what to make of that. But anyway, you have 2 dimensions. They're interesting computations.
Yeah, indeed. In particular, one can do this, for example, in the old duality between 2-dimensional string theory with 2-dimensional target space and C=1 matrix model.
Yes.
And things like that. So yeah,
I've looked at those papers a little bit. It's fascinating, but I wish one knew how to generalize it. But
indeed, the computation I have in mind is a short paper by Hartnell and a student of his.
Yes.
And one can kind of sort of generalize this for inhomogeneous CFTs. So if one has a CFT on a curved background where the metric is just dx squared plus f of x dt squared, and one computes, okay, if I'm not claiming this is rigorous, but there is some way to generalize this in homogeneous CFTs, where then the UV cutoff epsilon is replaced by 1 over this function f of x. And indeed, in the context of the C=1 calculation, one can really match this and find a description of the C=1 matrix model as an inhomogeneous CFTs for these free fermions. And the G string of x really comes from this factor in the metric of the inhomogeneous CFT. Yeah. It's nothing really amazing, but it's a...
I see. That's interesting. Well, it makes a lot of sense that string theory would cut off the divergence in the entanglement entropy. And
yes, of course.
Beckenstein and Uglum gave a nice heuristic argument for that once, which has to do with closed strings that are partly outside the horizon and partly inside. But nobody's been able to make it more precise. Zahar, do you have another question? Your hand is up, or is that from before?
Thank you.
Okay.
Yes, I have a small question.
Okay.
About the interpretation of Cassini's bound.
Yes.
Improving upon Beckenstein's bound. So if I have a system of size R and I just move it further away from the Rindler horizon,
yes,
clearly the formula would have to be reconsidered because I have now a explicit dependence on the distance from the Rindler horizon.
Well, the bound becomes less interesting because curly increases without the entropy changing very much. So to make the bound as interesting as possible, you move your system as much as you can to small x. For Cassini's bound to be similar to what Beckenstein said, you have to move the system to the smallest x you can. So if the system has a small size, you move it to its left end as at x=0. And then Cassini's bound coincides with what Beckenstein said, up to a factor of order 1, basically.
Yeah.
But it is, I do want to stress something that I said. It was, I think it was the last sentence. I think it was the last sentence on my last slide. Something really interesting is that it's possible for both terms in the equation to be negative, and the equality is still true. So that shows that it's valid way outside the region where thermodynamics makes sense. Beckenstein was thinking in terms of thermodynamic concepts. But here we have an arbitrary quantum state. And when it's extremely quantum, you can make both the left and right-hand side negative, but the inequality is still true.
It was just not obvious to me that by moving the system to the right, you would make the bound less interesting. That was my question, because T00 is not positive.
Well, the integrated T00 is positive. So the integrated T00 is positive.
Right, but when you integrate it against X, it was not obvious to me.
Well, when you make X bigger, you make it X almost constant inside the body.
Right, but if the integral happens to be slightly negative, by pushing it much to the right, it might become much more negative.
No, it doesn't. It doesn't, because okay, at any given position, X has an average value at that point, and then there's a slope nearby. So the integral of X times T00, write it as the integral of X. If you move the center of mass of position L, if you add a constant to X, which is what you're asking about, you just change this integral by the integral of T00. And although it's true that the integral of T00 over the right half space isn't positive definite, for a state that's localized away from X equals 0, it is positive definite. It's the ordinary energy. So what you're doing is simply add, once you've shifted the position by a large amount, you will just be adding bound a multiple of the energy of the state.
Okay, so you must assume that the state is localized in the right region, and then it's okay.
The bound is universally true, but the interpretation, well, first of all, the interpretation that to match what Beckenstein asked is if the state is mostly localized at positive.
Okay, 100%.
And then the bound is as interesting as possible if you move the state as far as you can to the left while it's still being localized at positive X.
Thank you.
Sure.
Any other question? Okay, thank you once again, Edward. Let me stop the recording.